Every year, migratory birds navigate thousands of kilometers between their breeding and wintering grounds with remarkable accuracy and an error of even less than 5 degrees. But how can they exactly do this? In this video, we're going to unlock this mystery by reviewing Navigation with Quantum Entanglement by Matt O'Dowd. So, let's begin. Today, one of the challenges about popular scientific videos is that in a lot of cases they are being presented by people with not enough of relevant background knowledge. This video, however, was presented by a well-knowledge presenter who had enough of background in quantum physics. Matt O'Dowd is an Australian astrophysicist and an associate professor in the Department of Physics and Astronomy at the City University. We'll see during the video that he was very successful in describing the topic of quantum navigation in the most accurate way following the recent published papers. He starts the video by telling the story of a spy from UK who tried to send critical information from Vienna back to London using a pigeon called All Alone. Using scenarios is a great way to start the content, and Matt was very successful in doing so to attract the attention of audience to introduce such an important topic. So, let's see.
In the summer of 1943, a spy from the UK parachuted into Vienne, a French town 20 kilometres south of Lyon. There, the spy learned critical information from the French resistance about La Milice, a Vichy paramilitary group with orders to round up Jewish people for concentration camps and to assassinate resistance leaders. To deliver the information back to London securely and rapidly, the spy was sent with an unusual piece of technology, a pigeon named All Alone. The spy attached his message to All Alone and set her free. With unerring accuracy and speed, All Alone covered the 481 miles back to her perch in Staines, England, in less than 24 hours.
Alright, before giving any reviews on the content of quantum navigation, I would like to introduce this concept based on the most recent published work, and later I would compare them with what was presented by Matt. Migratory birds have an internal clock with an annual rhythm that tells them where to migrate. They have at least 3 different compasses. One allows them to perceive information from the position of the sun, another uses the patterns of the stars, and last but not least, the sense of magnetic field patterns of the Earth, which is called magnetoreception. In 1978, Klaus Scholten tried to understand this phenomenon. He believed that the compass relies on magnetically sensitive chemical transformations. At first, this proposal seems not to be doable, because the energy available from Earth's magnetic field is millions of times smaller to be able to break the bonds between atoms in molecules. But Scholten was aware that short-lived chemical intermediates known as radical pairs have such unique quantum properties that make their chemistry sensitive to magnetic interactions. New measurements support the idea that a protein in bird's retina called cryptochrome 4 could serve as a magnetic compass, and its magnetic sensitivity relies on quantum mechanics. Cryptochromes are composed of chains of amino acids folded up into complex 3-dimensional structures. Inside cryptochrome, there is a molecule called FAD that, unlike the rest of the protein, absorbs blue light. There's also 3 or 4 tryptophan amino acids stretching from the FAD out to the surface of the protein. Immediately after the FAD absorbs a blue photon, and an electron from the nearest tryptophan hops onto the FAD. The first tryptophan then attracts an electron from the second tryptophan, and so on. In this way, the tryptophan chain behaves like a molecular wire. The net result is a radical pair made of a negatively charged FAD radical in the center of the protein and 2 nanometers away, a positively charged tryptophan radical at the surface of the protein. The resulting molecules, each with a lone electron in an outermost or valence shell, are called radical pairs, and their unpaired valence electrons are entangled, meaning some of their quantum properties are correlated, such as quantum spins of the two valence electrons in two separate radical molecules. And yay, that's it. Matt actually does a great job in describing the singlet and triplet states of radical pairs here, so let's see.
4 possible combinations for the spins. The first is the so-called singlet state, where the spins are pointing in opposite directions. We'll call them up and down. We don't know which electron is up or down, and this undefinedness is part of the whole entanglement deal. Simply opposite each other becomes a single state, hence singlet. The other 3 states are when the electrons have the same spin direction, either both up, both down, or a quantum superposition of both at the same time. These 3 are energetically equivalent, so together they make up a triplet state. If you have just one radical, its valence electron spin tends to stay fixed until disturbed by its environment, and Earth's magnetic field isn't nearly strong enough to influence the spin in that brief time. But in a radical pair, spin states will oscillate between the singlet and the triplet states. They do that evenly, even in the absence of a magnetic field, 75% of the time in the triplet state, 25% in the singlet. But even a weak magnetic field like the Earth's can affect the amount of time the radical pair spends in these states.
Alright, now both singlet and triplet states can undergo chemical reactions that transfer them into the signaling states. The signal state of the cryptochrome can then turn on a biochemical cascade and continue to bird's brain, where the magnetic information will be integrated with information from other directional cues and lead to a true visual sense of magnetic field orientation. Okay, until here, most of the concepts that were covered by Matt were based on the latest publications and what we know so far about quantum navigation in birds. During the video, however, he didn't really dive into the biological side and try to generalize it. It is reasonable why he didn't want to go into the biological side, but the fact is there are more than 10 types of cryptochrome proteins existing in the bird's eyes, which have very different functions, from light-activated switches and circadian rhythm functions to magnetoreception and so on. But we know that only a specific cryptochrome, called cryptochrome 4, plays a magnetoreception role, only in migratory birds.
I won't delve too far into the biology or chemistry here, but there is a protein that does all of this. It's called cryptochrome. Experiments since Scholten's proposal have shown that it's possible to affect cryptochromes with a weak magnetic field and get that characteristic change of rate of chemical reaction.
I also think he could have talked about the role of cryptochrome in non-migratory birds, as it remains an open question for audience that what would be the role of cryptochrome in non-migratory birds. Okay, now let's look at how he finishes the video.
We need to perform incredibly careful experiments in highly controlled environments. Ideally, isolated systems of very few particles, perhaps in a vacuum or near absolute zero temperature, not in the warm, wet, and messily macroscopic environment of a living organism. Quantum entanglement is very quickly destroyed in such environments, but birds may have found a workaround. The radical pairs only need to stay entangled for a microsecond for this mechanism to do its job, because after the entanglement is destroyed, the subsequent chemical reactions remember the quantum state and so remember the magnetic field.
He's totally right here. One factor making interpretations of the results more difficult is that experiments on isolated proteins don't really match the conditions in bird's eyes. For example, scientists think that the proteins may be aligned in some specific directions within the retina that would be different when they isolate the proteins. To further illuminate the process, the researchers hope to perform future studies on actual retinas to get a literal bird's eye view. Okay, that was the end. Thank you so much for watching this video, and here are the references that I used.